Okay, you see this thing every single day. The classic plastic bottle. It's everywhere, it's super convenient, and it's a massive environmental headache. But what if we could totally reinvent it from the inside out? Let's get into it.
Just imagine for a second, what if we could make a new kind of plastic that starts its life as a plant, not as petroleum? And what if this new plastic wasn't just a substitute, but a genuine upgrade? We're talking stronger, better with heat, and way better at keeping your drink fresh. Well, that's not some far-off sci-fi dream. It's actually happening right now, thanks to some really brilliant chemistry.
So to really get why this new discovery is such a game changer, we first have to wrap our heads around the problem we're trying to solve. It all comes down to our deep dependence on fossil fuels, not just for gas in our cars, but for the very stuff we make things out of.
You know that clear, crinkly plastic in soda and water bottles? That's called PET, and its family tree traces directly back to petroleum. Every time a new bottle is made, we're dipping into a resource that's running out and, propping up the whole fossil fuel economy.
But there's this incredible alternative on the horizon called PEF. It's a bioplastic, and when you put them side by side, it's not even a fair fight. PF, which we can make from plant sugars, is just better. It's got a much stronger barrier, meaning it keeps oxygen out and the bubbles in way more effectively. It can handle more heat, and of course, it comes from renewable plants. It's just a better bottle, period. So, that begs the question, right? If PPF is so great, what's the catch? Why isn't every bottle already made of it? Well, that's where we hit the big roadblock. Actually making this stuff from plants has been a massive chemical puzzle for a long time.
The whole process hinges on one critical molecule, FDCA. This stuff is so important that the US Department of Energy actually put it on their top 12 list of essential chemicals for building a whole new green plant-based economy. So the mission is clear. If you can figure out how to make FDCA cheaply and efficiently, you unlock the future of bioplastics.
So here's the basic game plan. Scientists start with a chemical called HMF, which they can get from sugars found in plants. Then they use a chemical reaction, an oxidation process, to turn that HMF into our golden ticket, FDCA. On paper, it looks simple enough, but step 2, that's where the whole thing just grinds to a halt.
For decades, this one chemical step has been the bottleneck, the big one. The process was just too slow, created too much waste, and was way too expensive to ever compete with the rock-bottom price of petroleum plastic. The dream of a better bottle was basically trapped in the lab.
And why so expensive? Well, because the materials needed to speed up the reaction, the catalysts, were all precious metals. I'm talking about gold, platinum, palladium. You can't exactly build a global-scale plastics industry on materials you also use to make jewelry. It's just not realistic.
Okay, but this is where the story gets really good. This is the breakthrough. A team of scientists came up with a totally new catalyst, a smarter, much cheaper recipe that doesn't need a single flake of gold or platinum.
And just a quick refresher, what exactly is a catalyst? The best way to think about it is like a chemical matchmaker. It grabs the molecules, gets them to react together much faster than they would on their own, and then it lets go, ready to do it all over again, millions of times.
So what's in this new secret sauce? Instead of precious metals, the main ingredients are iron and cobalt, two metals that are super common and abundant. They anchor these metals onto a clever carbon support structure, and then they add a little bit of phosphorus as the secret ingredient. It turns out, that phosphorus gives the whole thing an incredible performance boost.
And get this, the way they make the catalyst is also incredibly smart and green. They don't use a bunch of harsh chemicals or complicated steps. They literally just grind the solid ingredients together and then heat them up. It's simple, clean, and much better for the environment.
So, the recipe sounds fantastic on paper. It's cheaper, it's greener, but the million-dollar question is, does it actually work? Well, let's take a look at the results when they put this thing to the test. The results were pretty jaw-dropping. When they used the catalyst with only iron, they got a measly 4% yield of FDCA. Cobalt on its own did much better, almost 63%, but when they combined iron and cobalt in their new recipe, the yield shot up to over 78%. That right there is synergy in action. The whole is way greater than the sum of its parts.
But they didn't stop there, because that's what great scientists do, right? They knew they could probably do even better. So they started fine-tuning everything, the temperature, the pressure, all the little details, to see just how high they could push that number.
And they nailed it. Under the best conditions, they hit an incredible 91.6% yield.
But honestly, the even bigger news might be this. They got 100% conversion of their starting material. That means every last bit of HMF got used up. There's virtually no waste. That's the kind of insane efficiency you need to take something from the lab to the factory.
And this wasn't just a fluke. You can see here how the reaction played out over 24 hours. It just steadily and reliably climbed that peak yield. This shows that the process is stable and controllable, exactly what you want for manufacturing at a massive scale.
So let's just recap all the wins here. The reaction happens in plain old water, not some toxic solvent. The oxidant is just clean oxygen from the air. And, this is huge, the catalyst can be reused. They showed it still worked great after at least 3 cycles, which makes the whole thing even cheaper and more sustainable.
You don't have to take my word for it. The scientists themselves summed it up perfectly. They've found a genuinely sustainable and efficient way to make FDCA, the key that could finally let us mass-produce these superior plant-based plastics. And that just leaves us with this one big final thought. This is about more than just one plastic bottle. This is a perfect example of how smarter, greener chemistry, using common, everyday materials and clean processes, could be the key that helps us finally move away from fossil fuels and build a truly sustainable circular economy.